Swayam Prabha. Digital India. Educated India.
Welcome friends to this NPTEL online certification course of environmental soil chemistry, and today we are going to start our week 4 or module 4 lectures, and the topic of this module 4 is soil solution, solid phase equilibria and sorption in soils. So, in this week we will be covering very important aspects of different soil chemistry aspects, and we will be talking about different solubility, and then we will be talking about different adsorption processes, adsorption isotherms, and we will be also talking about different diffuse double layer models and different electrokinetic phenomena. For example, we will be talking about zeta potential. So, this week is very important as far as the soil electrochemistry as well as soil solutions and their dynamics are concerned. So, in this week we will be basically talking about these concepts. We will be covering this concept. First of all, we will be talking about measurement of soil solution, how we generally measure the soil solution. Then we will be talking about the speciation of the soil solution, and then we will be talking about ion activity and activity coefficients, and then we will be talking about dissolution and solubility processes. Then we will be talking about surface complexes, what type of complexes generally different metal forms with the soil surface, with the soil particles, and then we will be talking about adsorption isotherms, then equilibrium based adsorption models, then we will be talking about sorption of metal cations and sorption of anions, and then surface precipitation we will be talking about, and finally we will be talking about speciation of metal contaminated soils. In this first lecture, basically we will be covering the measurement of soil solution, and we will try to cover the speciation of the soil solution. So, let us start. So, what is basically soil solution? Soil solution is the aqueous liquid phase of soil, and it solutes, and it is a basically in case of soil you can see the major solutes are the ions which are present in the soil solution. They may be cations, they may be anions. Okay. So, these ions occur either as free hydrated ions like aluminum 3 plus, or as various complexes with organic and inorganic ligands. So, what are the ligands? We have already covered in our previous week lecture when we talked about the chemistry of soil organic matter. So, you have a basic idea about the ligands and how they form, and these ions either occur as the free hydrated ions like aluminum, which we also discussed in our last lecture, and as various complexes with organic inorganic ligands. The ligands could be either organic or inorganic. So, total ion concentration in soil solution thus can be considered as a cumulative, it is basically sum of the free ions and as well as the complex ion. And various complex chemical reactions interact with each other, through the soil solution. So, these are some basic points about the soil solution. So, let us talk about the inner and outer sphere complex. Now, inner sphere complex is basically when no water molecules are present in between the metal ions and the ligand, and they interact directly in the solution. As we can see here, basically, and they are also tightly bound. So, this is the inner sphere complex, and you can see that here these iron atom is basically directly linked with or this metal ion or iron is basically linked with these ligands, and without the presence of water molecules in between these. So, although you can see the water molecules are present surrounding the iron, but in the link which is directly working with the ligand, there is no presence of water molecule. And now outer sphere complex is water molecule, when water molecules forms bridge between the metal ligand, metal ion and the ligand. So, as you can see here, this is again the metal ion which is surrounded by 1, 2, 3, 4, 5, 6 water molecules, and these water molecules basically forming the hydrogen bond with these ligands. So, due to the presence of this water molecules as a bridge between the metal ion and the ligand, they are called as outer sphere complex. So, this is inner sphere complex and this is the outer sphere complex. Remember, the outer sphere complex are not tightly bound as inner sphere complexes, because inner sphere complex the bond is directly between the ion as well as the ligand. However, here the water is acting as a bridge. So, obviously, the strength of the binding strength varies from inner sphere complex to outer sphere complex. So, in case of inner sphere complex and outer sphere complex, remember that an uncharged outer sphere complex is referred to as an ion pair. For example, in case of calcium and sulphate, ions are known as to form an ion sphere of calcium sulphate. So, soil solution consists of a variety of ion species either in complex or non-complex forms. Now, what is the dynamics of equilibria reaction in the soil? It will be very clear if you see in this diagram, and one thing is clear that the solution in the soil solution we have already discussed, it is basically the free ions as well as the complex ion, and these free ion and complex ion can move in different pools and different pools, and these are basically mentioned here. So, let us start with the first of all, the plants can take up the nutrients or ions from the soil solution, which we already see here by pathway 1, and at the same time plant exudates a substance secreted by the plant. So, basically they reside into the soil, and from there will be movement of ion in the soil solution. Second, third is ion can move, ion from the soil solution are sorbed on the organic and inorganic components of the soil. So, sorption means it is basically either there are two types of sorption, either adsorption or absorption. Now, in both these conditions, absorption is an internal phenomena, however, adsorption is a surface phenomena. So, the ions in the soil solution get sorbed on different organic and inorganic components of the soil, and however, these sorbed ions are released back into the soil solution also. Now, so these are the first first 4 pathways through which the ions can move from this soil solution to different pools. Now, also if the soil solution is supersaturated, let us consider the soil solution is supersaturated, then with mineral in the soil, then mineral basically precipitates. So, this 5th pathway is basically showing the precipitation of the ions in the forms of solid phases and minerals, and reversively, if the soil solution is undersaturated with any minerals in the soil, the mineral dissolves and then go back to the soil solution to maintain an equilibrium until this equilibrium is reached. So, you can see this is how these ions move to the solid precipitates and further dissolves to maintain dissolves to go to the soil solution to maintain the equilibrium. Now, so first 6 pathway we have discussed. Now, 7 says that ions in the soil solution can be transported through the soil into groundwater or removed by surface runoff. So, the ions can move directly to the groundwater through solute transport, and then from there they will they can and also they can be removed through surface runoff, and in the reversibly through evaporation and drying, the upward movement of ions into the soil solution may also happens through the pathway 8. Now, pathway 9 says that microorganisms can remove ions from the soil solution, because microorganisms are known for different chemical conversion of ions. So, they basically take some different ions and then convert them. Now, when the microorganism die, organic matter decomposes and ions are released into the soil in the form of mineralization. So, it can be either immobilization. Ninth pathway is showing basically the showing the immobilization in the plant into the organic matter and microorganisms body, and when they die there will be mineralization, so that these mineral further goes to the soil solution. And 11th pathway is basically showing that the gases may be released to the soil atmosphere and gases may be dissolved in the soil solution. So, this is another way through which the the ions can move from soil solution to the atmosphere and vice versa. So, this is basically giving an idea about the movement of different free and complex ion from the soil solution to different pools, and their movement and their reversible movement directly back to the soil solution. Now, when we talk about the measurement of soil solution, there are two factors we need to consider. One is called the intensity factor, another is the capacity factor. Now, what is the intensity factor? Intensity factor basically says the concentration of a particular ion in the soil solution, whereas the capacity factor basically denotes the ability of solid components in the soil to resupply an ion that is depleted from the soil solution. Now, we have already seen the capacity factor in the last diagram, wherever we have seen that the concentration of a particular soil solution, particular ion goes down into the soil solution to maintain an equilibrium from the precipitate or solid phase. Precipitate minerals or solid phase, the minerals can dissolve and then they basically supply that ion back to the soil solution to maintain an equilibrium. So, that is the capacity factor. Now, intensity factor measurement is very important in predicting and understanding various reaction in the soil environment. However, measurement of intensity factor in situ is very difficult. Obviously, the intensity factor talks about the concentration of a particular ion, which is in practice very difficult to measure in situ, that means on site. So, the actual concentration of an ion species in the soil solution varies with changes in soil moisture content. So, these are some of the factors which basically says that intensity factor calculation is little bit problematic. So, the three main types of techniques we generally follow to extract the soil solution as per as Adam and Old who have given different process. First of all is called the displacement technique, second is called the centrifugation, and so the first one is displacement technique, second one is centrifugation, and the third one is called the saturation process or saturation extract. So, we will see them one by one. So, let us first concentrate on the displacement process. So, displacement process basically we as a soil scientist we generally use column displacement to measure the concentration of ions or intensity factor. For example, a filled moist soil, as you can see in this picture, a filled moist soil is packed into the glass column and displacing solution is added. So, you can see it is a leaching solution or displacing solution. So, we are adding this displacing solution at the top of the packed soil column through peristaltic pump, and these leaching solution or displacing solution, which is basically essentially water, is collected. I mean basically when we are passing this leaching solution will pass through this soil column and then will be collected at the bottom. So, this is called the displaced solution, which is essentially water. So, basically they collect at the bottom of the glass column and analyze for its concentration. and this is the most reliable method, however tedious and time consuming. So, here you can see basically we are adding a leaching solution. This leaching solution is leaching down all the elements or all the ions which are present in the soil, and before that the soil is packed inside this glass column, and then these ions are moved down or leached down and basically collected at the bottom, and then further we are measuring. So, this is the most reliable method, however they are tedious and time consuming. So, the second method is called the centrifugation method. So, centrifugation involves the application of centrifugal force to separate particles based on their size, shape, density, viscosity and rotor speed. Generally, we apply more than 1 megapascal of pressure from from 30 minutes to around 2 hours. So, more dense components move away from the axis of the centrifuge and vice versa, and the larger the size and density of the particles, the faster they are separated from the mixture. As you can see, before centrifugation you can see the particles are suspended, however after the centrifugation you can see the particles are settled down and forming a pellets, and obviously more dense components, as you can see, they will move away from the axis and then they will form the pellets. So, in this way we can separate out different different particles based on their size, shape, density, viscosity and rotor speed. So, the centrifuge also, in case of centrifuge, there is a term called immiscible liquid. So, when two liquids are completely insoluble in each other, they are known as the immiscible liquid. So, though it is a mixture, two different phases are present in the liquid separately. So, during centrifugation, an immiscible liquid such as carbon tetrachloride or ethyl benzoyl acetate is added to the soil to physically remove the soil solution. As you can see, basically in case of centrifugation, we apply these liquids such as carbon tetrachloride or benzoyl acetate or ethyl benzoic acetate to the soil to physically remove the soil solution without being mixed into the soil solution, that is essentially water. So, the immiscible liquid passes through the soil and then the soil solution is displaced upward. Since these two, since these two liquids are immiscible to each other, they will not mix, they will not be mixed with each other, and as a result they will displace each other. So, when we are passing this immiscible liquid, that passes through the soil and displace the soil solution. So, the displaced soil solution is collected and filtered through a phase separating filter to remove the traces of immiscible liquid, and further it is filtered through a 0.2 micron membrane to remove the suspended clay minerals. So, you can see in this way, by adding a displacing liquid or adding a immiscible liquid, we are basically replacing the soil solution. Not only the replacing soil solution, then by filtering we are removing the traces of the displacing solution, and also we are removing the suspended clay particles, and this is basically relatively simple, and equipments are also easily available in most of the chemistry labs. Now, the third one is called the saturation extract. So, distilled water is added to the soil in a beaker and stirring with a spatula, as you can see here, and beaker is tapped occasionally to consolidate the soil water mixture, and saturation is achieved when the soil glistens. As you can see in this picture, the soil is glistening. So, you can see that the soil is saturated, that means all the pore spaces are filled by water, and then from the and also during the saturation soil drops freely, soil drops freely from the spatula, and the soil flows together with the separated with the with the spatula, and then it is then allowed to stand for 4 to 16 hours prior to extraction to basically homogenize and also to equilibrate, and then the soil paste is then transferred to the funnel containing the filter paper, and then the funnel is connected to a flask. Generally we and then this funnel is connected to the flask and we apply vacuum, then the filtrate is basically collected. So, what happens? Again, step by step we are basically adding the water, making a saturated paste, keep it for equilibration for 4 to 16 hours. After that we are putting into the funnel and then applying the pressure to suck out the dissolve ions through the leaching solution or through the solution which is basically filtered, and then we are basically measuring the concentration of ions in that filtrate. So, this is how the saturation extract basically occurs. Now, average ion composition of soil solution, obviously we have seen that calcium is the most predominant metal cations in the soil solution. However, nitrates, chlorides, sulfates are the most common anions or ligands in acidic soil, and also remember that the carbonate is the most predominant anion in the basic soils, and basically in the basic soil you will see the precipitation of calcium carbonate. Now, the speciation of soil solution, it basically refers to the determining the distribution of the ion in their various chemical forms. So, when we can determine, okay, these are the ions and these are their forms which are present in the soil solution, we can tell that we have made the speciation of the soil solution. Now, ions in the soil solution can form a number of species due to the hydrolysis, complexation and redox reactions. You have already know what is hydrolysis, what is complexation and redox reaction. Let us see. Now, let us first discuss the hydrolysis process. Now, hydrolysis involves the splitting of an H plus ion or proton from a water molecule which forms an inner sphere complex with a metal ion. So, the general hydrolysis reaction from a hydrated metal ion is given as MH2O X N plus, and from there we can get these two species, where this is basically the hydrated metal ion. This is the hydrated metal ion, and N basically says the charge on the metal ion, where X is basically the coordination number, and here Y is basically the number of protons released into the solution, and so basically, and this is the intensity factor. So, let us see some important based on this. If we see the complexation, the another process, in general the complexation reaction between a hydrated metal, and a ligand which is termed as L1 minus to form an outer sphere complex is, this is the outer sphere complex. So, basically this is the hydrated metal plus a ligand forming an outer sphere complex, where A, B, C and basically A and B, no, there is no C and D. A and B are the stoichiometric coefficient. We have already discussed stoichiometric coefficient. These are the degree to which the chemical species participate in a reaction. So, this is the complexation, and in case of speciation the soil solution, analytically it is little possible to determine all the individual ion species that can occur into the soil solution. I have already told you that measurement of in situ, measurement of intensity factor is somewhat difficult. So, to identify the species, ion association or speciation model must be applied using the total concentration data for each metal and ligand in the soil solution. So, let us see how we do that. So, a mass balance equation, let us consider a mass balance equation for total concentration of a metal ion. Let us consider this metal ion, this is the metal ion in the solution phase is given by, this is the mass balance equation, where these Mn plus is basically concentration of the, this Mn plus is basically concentration of free hydrated metal ion species, and this mml is basically concentration of metal ion associated with the remaining metal ligand complexes. So, when we combine these two forms, one is the hydrated metal ion species, another is the concentration of metal ion associated with the remaining metal ligand complexes, we will get basically the total ion which is present in the total of that particular ion which is present in the soil solution. So, the ligands can be inorganic anions or humic substances like humic acid and fulvic acid. We have already seen that previously. Now, so similar mass balance equation can be formulated for total concentration of each metal ligand in the soil solution. So, if we consider there are several elements or several metals which are present in the soil solution, we can develop this mass balance equation for individual metals. So, each metal ligand complex has an associated conditional stability constant, which you have already seen during our discussion during the organic chelates. So, the conditional stability constant varies with electrolyte concentration. We have also seen that. However, this conditional stability constant of inorganic complexes can be related to thermodynamic equilibrium constant K0. Now, this K0 is independent of electrolyte composition at a particular temperature and pressure. So, although this conditional stability constant varies with electrolyte concentration, this K0 or thermodynamic equilibrium concentration constant K0 is basically independent of electrolyte composition at particular temperature and pressure. So, what is the relationship between these two constant? One is K condition, that is conditional stability constant, and then thermodynamic equilibrium constant. So, basically for any reaction, if you see, that is A, B, C, D are basically the stoichiometric coefficients. So, at thermodynamic equilibrium, a thermodynamic equilibrium constant K0 is basically given by this formula, where this A, B, C, D, as you know, these are the stoichiometric coefficients, and these A, B, C, D are chemical species, whereas this parenthesis refers to the chemical activity of the each species. So, chemical activity of C to the stoichiometric coefficient power, and then the chemical activity of D to the power stoichiometric coefficient corresponding to stoichiometric coefficient by the concentrate or the chemical activity of a power to the power of their corresponding stoichiometric coefficient at the chemical activity of B with to the power of their corresponding stoichiometric coefficient. So, this is the relationship. However, so how to get the relationship between K0 and K condition? So, the thermodynamic equilibrium constants are excuse me, let me just, if we just go back lifestyle. So, the thermodynamic equilibrium constants are independent of concentration of the electrolyte. We have already seen, because they are expressed in terms of activities rather than concentration. Since they are expressed in terms of activities, as you can see, rather than concentration, so they are independent, they are basically independent of concentration of the electrolyte. Unfortunately, then activities of the ions in the salt solution cannot be measured directly, which we have already discussed. So, fortunately, the activity and concentration of an ion in a solution has a relationship, and this relationship is basically this one. So, if you see that the activity of a particular ionic species is basically the multiplication of the concentration of that ionic species in the solution in mole per liter into their single ion activity coefficient for species B. So, if we multiply the concentration of a specific ion in the solution with their corresponding ion activity coefficient, then we can get their their activity of that particular specific ion. So, rewriting the previous equation using concentration rather than activities, we can see that we know that this is the equation. So, we can just rewrite this in terms of this this activity. We can express this is a multiplication between the concentration and the activity coefficient, concentration activity coefficient, concentration activity coefficient, concentration activity coefficient, and from there we can simplify this, and now we know that this term equals to the conditional stability constant. So, this is how this K0 is basically conditional stability constant multiplied by this fraction. So, conditional probability stability constant is also known as conditional equilibrium constant. So, a thermodynamic equilibrium constant is equal to the conditional equilibrium constant multiplied by this fraction of intensity factor. So, basically the ratio of activity coefficients, as we have seen, relating the K condition to the K0. So, as we have seen from here, from this equation. So, the value of the activity coefficient, and hence the ratio of the activity coefficients, which is this, changes with the changes in electrolyte composition. So, in very dilute solution, the activity coefficients approaches to 1. So, this total fraction will approaches to 1. Hence, in that condition, the thermodynamic equilibrium constant will equal to the conditional equilibrium constant. So, in case of very dilute solution, the activity coefficient approaches 1, so this fraction becomes 1, then conditional stability constant and conditional equilibrium constant equals to the thermodynamic equilibrium constant. So, if we let us see an example using the mass balance equation and the conditional equilibrium constant, we can speciate a metal ions in the soil solution. So, let us solve a problem. Let us calculate the concentration of a different calcium species present in the soil solution from a basic soil. So, assuming a pH of 7.9, the total calcium concentration is 3.715 multiplied by 10 to the power minus 3 mole per liter. So, we assume that calcium occurs as free hydrated calcium ions as well as complexes with inorganic ligands like carbonates, sulphate and chloride, like calcium carbonate, as you can see, calcium bicarbonate, calcium sulphate and calcium chloride. Let us assume this. So, using the mass balance, so the sum of all the complex forms, the sum CAT, if we consider CAT is the sum of free and complex forms, then we can express this in this through this equation, where CAT equal to the free calcium plus the complex form concentrations. So, where brackets indicates the concentration in mole per liter. So, each of these above 4 complexes, this 1, 2, 3, 4 complexes is a conditional stability constant given by this K1 condition, K2 condition, K3 condition, K4 condition. We already know this from our discussion from the soil organic matter. Now, if we take the calcium outside, which is a common factor in this CAT equation, then we can get this form. So, the Ca, if we consider Ca, then we can get this form. From there, we can have this simplification, that is 1 plus K1 condition multiplied by CO3, 2 minus K2 condition multiplied by bicarbonate concentration, K3 condition multiplied by sulphate concentration, and K4 condition multiplied by chloride concentration from the previous relationship, from the equation of the stability constant. From the equation of the stability constant, we can get this relationship by taking the calcium ion in common, or concentration of calcium in the common factor. So, the mass balance equation are thus transformed in coupled algebraic equation. So, we have seen that this is a algebraic equation. So, this mass balance equation are thus transformed into coupled algebraic equation with the free ion concentration as unknowns by substitution for the complex concentrations. So, the algebraic equation can be solved iteratively using successive approximation to obtain the free ion concentration by using number of possible computed equilibrium models. So, these algebraic equations can be solved by help of a number of computed equilibrium models which are present. Now, this we follow a iterative approach like Newton-Raphson's approach or computed equilibrium model to solve this for free calcium ion concentration. Now, speciation of the soil solution, if you consider, the computer models have thermodynamic database. All these computer models have their thermodynamic database containing the equilibrium constants for aqueous complex species. So, the free ion concentration obtained from the iterative approach can then be used to calculate the concentration of the metal ligand complexes. For example, in this case, the complex of calcium bicarbonate forms this reaction. We can see that Ca2 plus H plus CO3 2 minus, we can see this is a calcium bicarbonate. So, from there we can basically calculate. Now, we know this thermodynamic or equilibrium constant. This is the equilibrium constant or equilibrium stability constant, that is 9.33 into 10 to the power 10. We have already know the value. from there we can get this equation, and from there we can we can solve the substituting this K2 condition into and solving this calcium bicarbonate concentration. So, let us wrap up here, and the next in the next lecture we will start from here, and I will show you how we can use these computer models for inputting these different conditional stability constant to solve the or to basically calculate the total concentration of a particular element in the soil solution. Let us wrap up here, and from the next in the next lecture we will be discussing that. Thank you.